Welcome everybody. Good to have you here. This presentation will be an introduction to the Waratek Cloud Virtual Machine for Java. This is a brand new Java virtual machine. If you haven't seen it before, it's not like any other Java virtual machine that you've used. We seek to solve a real big problem that people are starting to recognize Java has. People who run a lot of Java applications, want to run many Java apps on a single server, they start to recognize that Java has some issues. It has some challenges as a platform, and particularly as a virtual machine, it has some issues it needs to deal with. And what's very exciting is, and the product we'll look at here, is a very special Java virtual machine designed to solve those pain points. We'll describe what those pain points are. We'll then see some screenshots of what essentially is an interactive session rather than doing it interactive here. I've just got some screenshots of that session. If you call by our stand afterwards, we have an interactive laptop set up where we can run code on the fly. Code does always speak louder than words. And then at the very end, we'll introduce a real use case, someone who's been playing with the Waratek Cloud VM, his experience with that, he'll talk around that. So some exciting discussion. So really to set the scene and to introduce the Waratek Cloud VM, this is a very special Java virtual machine, and it's special for this very simple reason, that it's a Java virtual machine that's designed to virtualize Java applications. And we say that in essentially the same way that VMware would describe the way they do virtualization for operating systems. So we virtualize Java applications to virtualize them in a similar way to the way a hypervisor virtualizes operating systems. Why do we do this? So there's a few problems with Java, and some of these things we know they are becoming increasingly talked about. Java is 15 years old, predates cloud computing, it predates even server consolidation and the hypervisor initiatives of the late 1990s and early 2000s. Java EE application servers have this interesting paradox. While on the one hand, they're designed to run multiple applications, multiple web apps, or multiple EAR apps, in practice, they almost never do. How many people here would be comfortable or happy deploying 10 WAR files from 10 individual programmers you don't know or trust onto a single instance of Tomcat, and be confident that one WAR file won't chew up all the memory, use up all the CPU? And the answer is systems administrators and operators today aren't. They're not confident doing that. And so as a result, what do? We have this situation which we can describe as application server sprawl, where because of that limitation, the lack of multi-tenancy within the JVM, within the Java environment, we give every single WAR file its own Tomcat, every single Tomcat gets its own JVM. And this really comes now to the root problem, that for people who run a lot of Java applications, they have a problem consolidating Java well. Because Java is not multi-tenant, every application gets its own virtual machine, and every time you start a Java virtual machine, you go ahead and you allocate a great big heap of memory for that Java application. But then the application that's hiding inside only uses a part of that heap, is not using all of it. Now that's fine if you have one application or two, but if you start running 20 or 30 or 50 or 60 or 70 applications on a single server, separate Java applications, that means 70 JVMs. That means that you've got 70 different heaps with a large portion of memory that's allocated and assigned and reserved by the operating system, by the JVMs, but not being used. And that unused memory within the JVMs is rarely, depending upon the garbage collector used, rarely, if ever, returned to the operating system or the hypervisor to be allocated elsewhere. So kind of problem number one that people experience, the systems administrators experience, is that running up many Java virtual machines, I have this upper bound of memory utilization that I hit. It's problem number one. Secondly, if I start running 50 or 60 or 70 separate JVMs on a single server, that means with a modern JVM today that I have 50 or 60 concurrent garbage collectors running in the background. I have 50 or 60 JIT compilers. And so that's an awful lot of compute time and memory time spent on actually not executing the application, which as a business is what I'm actually here to do. So this is one of the major problems with Java. We see that there are some initiatives inside the Java community. Multi-tenancy is on a roadmap for inclusion in Java 9, but Java 9 is 2015 story. So these pain points are not being addressed today, and there are others we start to build on that, that Java suffers from. So kind of this is just a further elaboration of the point that because the Java virtual machine is treated as a strict quota of CPU and memory, the ability to control and provision, have elastic memory allowances between virtual machines starts to become quite difficult. How can I take memory conveniently from one JVM, shuffle it, move it to another JVM? How can I do that elastically? How can I do that in real time with essentially no delay in that migration of the memory allowance from one virtual machine to another? There are some tools and efforts from different parties and initiatives to do that in part, but there's no real good, solid, comprehensive solution built into a JVM today. This is really just a pet pet issue, I guess, for a lot of systems administrators and even dev guys is they say, the Java EE servers, which are the dominant way we run most of our enterprise Java applications today, they're not multi-tenant as what a hypervisor engineer might call multi-tenant. For that reason, if I deploy my 20 WAR files and my 20 EAR files on a single instance of Tomcat, I have no control in the JVM today. There is no API that can say these kind of things. Servlet number 7 in a shared Tomcat environment is only allowed to use 32 megabytes of memory, and its threads can only run on CPUs 7, 8, and 9, whereas servlet number 2 can run on CPUs 1, 2, 3, 4, and it can use 100 megabytes of memory. There's no API in Java today to do that. There's no API in Tomcat. And so as a result, we have that application server sprawl problem where we load a new Tomcat for every WAR file or a new JBoss for every AR file or whatever app server it is that you might be using. And then lastly, if there were solutions to these problems, if a good multi-tenant JVM existed, and in particular a virtualizing JVM, a JVM that does virtualization inside, then you'd also be able to change the way that you can consume Java as a user or provide Java as a hosting operator or as an infrastructure operator or a system administrator. And you'll be able to turn Java into a real service where you can build the Java used and consumed by the actually consumed CPU cycles. So you build CPU time on a similar metric to what we used to for electricity, gigahertz hours for CPU, gigabyte hours for memory, like kilowatt hours for electricity, if there was a JVM that was virtualizing and multi-tenant. And this is really the entree to introduce the Waratek VM, because these are the pain points that we begin to address and we start to bring in the Waratek Cloud VM to address. And the technical architecture is very simple to what the Waratek Cloud VM does. It is something very unique for Java, though, and it's best described in the following way. The Waratek Cloud Virtual Machine for Java is a virtualizing JVM where we've built into the JVM core what is notionally a hypervisor. And so users and systems administrators can think of it and treat it as an application hypervisor for the Java platform. This virtualization engine, which is embedded inside the JVM, creates this facility within the Java virtual machine called Java Virtual Containers, or JVCs for short. And a Java virtual container is conceptually just like a Linux container, except it lives inside the JVM. It is razor thin. The memory overhead per Java virtual container is only 440 odd kilobytes of memory. That means a single JVM can have hundreds of these virtual containers, and each virtual container is a fully virtualized abstraction, isolated abstraction of the host JVM underneath. So that means in the diagram on the slide that, yep, you can fire up 64 JBoss instances in a single JVM. You can fire up 128 Tomcats. You can fire up Tomcat 4 and Tomcat 5 and Tomcat 6 and Tomcat 7 all side by side concurrently in the same JVM because each version runs in its own JVC. So the isolation inside the Java virtual containers is complete, but it's also fully TCK compliant. It runs all the applications. You can use sun.mist.unsafe. You can go system.setout in VC2 and change your output stream in VC2 and have no effect on VC3. So they're fully virtualized and abstracted. The JVM manages and runs these Java virtual containers then for the purposes of consolidation and density. Because at an overhead of only 440 odd kilobytes, it means a single JVM can run a lot more Java applications than 30 or 40 or 50 JVMs, each running their own Java application. And so this starts to drive up the consolidation ratios you can get for Java applications, drive up the density, improve your efficiency, and then with the features inside the JVC engine, start to make those applications do things that they have never done in Java before, such as every aspect of JVC execution is metered. So memory is metered in individual bytes, no surprise there. CPU is metered in individual hertz. That's singular consumed CPU cycles in hertz. We then use, it says on the bottom point, we then use the same formula that electricians use to calculate kilowatt hours to actually export data through management APIs for the gigahertz hour of consumed time that that application uses in a Java virtual container and gigabyte hours for memory. So, and we'll see a demonstration of that little at the end, and that's really exciting for people who have the challenge of running a lot of Java applications from either disparate users or disparate departments in large organizations. It gives them the facility to start to have a chargeback model that they haven't had before. And every aspect of JVC execution is independently isolated and controlled. As we'll see a little later, you can decide these kind of things about it on a per JVC basis. You can decide which CPU cores does the JVC run on. So you might have a server underneath with 24 cores, and you can say, I want VC number 3 to use CPU 7, 8, 9, and I want VC number 4 to use CPUs 1, 2, 3. In fact, all the same controls are built into the JVM for managing JVCs as we take for granted in hypervisors. And the real embodiment of that, the realization of that, is that one of the management facilities inside the JVM, not the only one, there's many, but one of the main management facilities is a command line interface called JERSH. And for administrators and for developers who are familiar with Virsh from the Red Hat world, used to manage KVMs and Xens and so forth, the Virsh command facility inside the JVM is command compatible with Virsh and is going to allow you to do the same things that you would do for your hypervisor VMs. Pin a virtual container to CPUs, set memory limits, change memory allocations on the fly. So you might have allocated 20 megabytes in the -xmm 20m command when you started a Java application, then decide after the fact, you know what, 20 megabytes isn't enough for this application. In a normal JVM, the way you solve that problem is you'd kill the application, you'd kill the JVM, and you'd start again. But if you have a Java virtual container, it's entirely dynamic if you want it to be. So you can just use command lines to say, okay, I want up the memory from 20 megabytes up to 100 megabytes while the application is running. And then start to enable all sorts of fancy features, which we'll see. And you get the same controls for network bandwidth and for I/O and sockets and file descriptors, essentially everything you can imagine. And what's perhaps another very exciting aspect, and arguably one of the most exciting aspects, particularly from a developer perspective, because everything we've talked about so far is really for the benefit of administrators and infrastructure guys. But where there is a developer conversation in this is where we look at the facility for extended virtualization or user-directed bespoke Java virtualization. And this is something that really has no precedence. This really is novel. And this is to say, hang on a minute, we've got all these EE servers that we love to use, and they are the basis for most of the enterprise applications we use today. But I can't turn around and treat JBoss or Tomcat as multi-tenant today. So I get that application service sprawl problem that we know of. But hang on a minute. In the Waratek Cloud JVM, it's a virtualizing JVM. We virtualize Java. That's how we do multi-tenancy and elasticity. Here's the kicker. The virtualization engine is itself written in Java. That means that there are inside the JVM APIs, commands, facilities that you can use as a programmer to actually tell the JVM how you want to virtualize something. So unlike a hypervisor VM, when you start a VMware ESX and you create a VMware image, a VM image, which you load an operating system in, that VM is dictated by the hypervisor. It doesn't change. There aren't APIs for a developer to say, I want a different kind of virtual machine, and tell the hypervisor how to change it. But in virtual containers inside the Cloud VM, that is the case. So using the extended virtualization facilities inside Java, you can start to create your own definitions of what virtual containers are. And you can change everything. You can change the way that we virtualize, you can change the way we do multi-tenancy, you can do simple things like, I want to change the file system that an application sees in a virtual container. Well, ordinarily, if you were to do that in a JVM, that would involve jumping into C code, say in OpenJDK, modifying the native libraries in java.io.file that back the Java.io file APIs to modify file.list routes and file.size and usable space and so forth. But here, what goes on? It's virtualized. So for me to change the file system that virtual container number 2 uses, all I have to do is write a pure Java class, make it implement a special interface called file driver, and then go virtual container 2 dot attach brackets my file driver implementation, and voila, transparently, Java.io file, file input stream, file output stream, random access file, memory mapped files, neos, whatever they may be, get virtualized onto your implementation of that file driver. So you can do chroots, you can do encrypted file systems, you can do file systems in zip files, remote file systems, but you can roll that out for network interfaces. You can have different network interfaces, VPNs, encrypted connections. You can do everything you can imagine that you'd want to do. But that's a simple example of extensible virtualization. Probably the more extreme example is where we actually virtualize a whole platform. And we'll see an example of that in a minute. And the diagram here shows that more extreme case, where by loading something called a virtualization driver into the Cloud VM, you can tell the JVM the following scenario. You can say, you know what? Rather than starting up Tomcat 20 different times with 20 different applications, what I want you to do, JVM, is I want you to start Tomcat, say, in virtual container number 1. And then I want you to know this virtualization profile, which I tell you through the virtualization driver, so that when Tomcat starts loading its WAR files, I want you transparently to Tomcat and transparently to the WAR files deploy each and every WAR file in its own separate virtual container on top. So if you think of an example where you've got Tomcat and 10 WAR files, you now have 11 virtual containers. 1 virtual container for Tomcat, and then 10 virtual containers for each WAR file. And that suddenly means that you have made, in an instant, Tomcat multi-tenant and fully controllable as if Tomcat had been designed from day 1 to do that, where you can start to do these things. You can say, servlet number 3 can only use 22 megabytes of memory. Its threads can only run on CPU 9. Servlet number 18 can use 250 megabytes of memory. It has an elastic memory allowance, and it can do all sorts of fancy CPU allocations. And so you can actually take control of Tomcat or JBoss or whatever app server has a driver written for it, and turn it into a multi-tenant platform, taking away the application service sprawl problem, taking away the need for multiple instances of that software stack, and consolidate it down to get even higher density ratios. So the extensible virtualization is very exciting, and it really shows, I guess, the power of doing virtualization in Java. Special JVCs are already available. There's a preview of a Tomcat virtual container. We'll see that on the slide now. There's a demonstration of it running in the booth, the Waratek booth in the exhibition hall. So that's a servlet virtual container for Tomcat. There is a JBoss virtual container for running EARs and WARs inside JBoss, and so forth. There are other environments where you can take for particular languages like Scalas or Closures or Groovies. You can say, I'm going to build a virtual container just for that kind of application where I'm going to change file systems and networks and even down to different levels, ultimately down to threads and so forth, to change the way you want to run that particular language, giving for the first time the community in an entirely pure Java, TCK certified way, the ability to change the behavior of the JVM. Very exciting stuff. And then as we look ahead, the virtualization really is only the tip of the iceberg of what the Waratek Cloud VM will start to deliver. When we think of virtualization at an operating system and infrastructure level, we now take for granted that it comes with a whole basket of management goodies. We have facilities like live migration. We have facilities like live snapshot. But while that's great at the hypervisor level, if you want to use live snapshot, live migration at that level, you're talking about the whole operating system. The whole operating system stacks. If you're running Red Hat, it's RHEL 6, and then it's the JVM, and then it's the app server, and it's the application on top. That's your unit of snapshot and migration. But with a virtualizing Cloud VM, you can do that same kind of management facility inside the JVM itself. So you can start to do things. You know what, I want to take Java Virtual Container number 3, and I want to live migrate it another node, or I want to snapshot it, and so forth. And perhaps the last thing, which is also worth mentioning kind of in the roadmap of where virtualization will go inside Java and inside the Cloud VM roadmap, is bringing in support for legacy JVCs. This is particularly of excitement to large organizations that have a lot of real estate running legacy Java applications. There's a lot of 1.4 Java apps kicking around out there. There's a lot of 1.5. 1.6 is legacy now or will be shortly. And so these applications are committed. They're running on old JVMs today, on old operating systems, on old servers. They're getting low utilization, low efficiency. And there's the roadmap for bringing them into a cloud environment without code change and without rewriting is very unclear. There's no real clear roadmap until you start doing virtualization in Java. And using Cloud VM, you can start to do things like, I want to create a virtual container, but you know what? Even though the host JVM underneath might be, say, version 1.7, I want to create a virtual container that's 1.4 or 1.5. And so by enabling that kind of a feature, you give a roadmap option for these people who have legacy Java applications to, without any code change or application change, they can migrate their legacy applications off their legacy systems onto a virtualized legacy environment, make those applications elastic, build them as utility services, and essentially cloudify those legacy applications at no effort for the organizations and administrators. So what does it look like? Because it doesn't behave like a normal JVM. And this is probably one of the first examples of that. When you type Java at a bash prompt in Linux, and you go Java enter with no command line parameters at all with a normal JVM, OpenJDK, hotspot, whatever it might be. You get the -x help information and you get dropped back to bash. But when you type Java enter without JVM, you get this. You actually get a prompt inside the JVM. And the prompt is called JERSH. JERSH is the name of the command line interface. And for people here who have a sysadmin background who work with KVM and work with Red Hat environments, they would know of VERSH, which sounds an awfully lot like JERSH. That's because it is. VERSH and JERSH are in fact command compatible. And JERSH has taken the same commands people are using to manage their KVM hypervisors and their Xen hypervisors today. And actually now we can use that to start, stop, suspend, resume, change memory allocations, pin to CPUs, all the things you do for hypervisor VM. But now we can do it to JVC tenants within a master host JVM. So that's kind of an example of it coming in. Now, here what we'll do is we'll start a few applications. These are just some screenshots. You can see a live running of this at the Waratek exhibition stand. But here is what it takes to say, for example, start a Java application. Now, JERSH is only one means, ultimately, of managing the Waratek Cloud VM. JMX APIs are provided behind the scenes. There are other facilities, there's libvirtdriver and so forth. But we'll just stay with JERSH for this example. So here we're running the class path, Cloud JVM Hello World, and Hello World in this instance prints out stats every second. So it's a TikTok-like application. That's fine. Now when we do list, this is the same list command as in VERSH, and it says to the JVM, tell me what JVCs you're running right now. And so using list, we see that we're running a JVC. It's virtual container ID number 2. It's running the Java Hello World application, and that's completely isolated. And from then on in, we're going to be able to reattach to the console the virtual container number 2, as we'll do now. So typing console2, we reattach to the console of that application, which is kept running in the background. That's why we see the Hello World count has jumped from 5 to 46. So the management interface keeps the applications running around in the background. But this is now where it starts to get really interesting, and it starts to show the real power of virtualizing Java, because that little hello world application that's running in JVC2, if we type in vcinfo or dominfo, both commands work, it asks the JVM, give me a real-time snapshot right now of some of the stats of this JVC now. And so here we see a sample of some of the data points the JVM tracks and collects on a per JVC basis. We see that even though the whole host JVM on this particular demonstration might have 1 gigabyte heap for the whole host JVM, virtual container number 2, running the hello world application, is only allowed to use 20 megabytes. Right now it's using just 1.1 megabytes. There are 2 class loaders, there are 221 classes, and the JVM is tracking this in real time. So the memory footprint for these JVCs, they can range in anywhere from size from 1 megabyte up to 99% of the JVM's host memory, if that's what you want to contribute it to. But there's something interesting being shown here, which is this facility called elastic memory. And this gets very exciting, and it shows the real power of JVCs, because unlike a JVM, if I'd made a mistake in setting -XMX 20 megabytes and giving a 20 megabyte allocation to hello world application, if I wanted to change that to 40 megabytes, it's just the set mem command. That's it. And 20 megabyte would go to 40 megabyte, and the application hasn't stopped, done anything. But I can also enable other features like allowed elastic memory, where I can say, you know what, I've got this particular application and it's got a very specific use case. I normally in production in a JVM, I'm giving it a 500 megabyte heap because sometimes it needs a 500 megabyte heap. Not because it always needs a 500 megabyte heap, just because sometimes. So in a JVC though, I have more controls about what I can do to run that application. What I can do instead is I can say, you know what, instead I'm going to give it a guaranteed reserve minimum, say of 100 megabytes. I always want to guarantee that this particular application has 100 megabytes of heap space in the JVM memory to use, but that's the only guarantee. Then what I want to do is give it an elastic memory allowance, a burstable memory capacity of an additional 400 megabytes, say, you can configure it there, that it can burst into, and then build rules around that, say, between 3 o'clock and 7 o'clock on a Friday afternoon. So you can turn these virtual containers into elastic units that can do things that JVMs don't normally do. Another example of kind of the measurement and monitoring controls that the JVM have built into it is mentioned up here in the gigahertz hours, the container CPU usage. The JVM tracks CPU usage, consumed CPU time of a JVC on a very fine-grained base on individual hertz, uses the same formula that electricians use for kilowatt hours to then expose gigahertz hours for consumed time. So you can start to put price tags to that, 1 cent per gigahertz hour, and on peak times 0.5% off, and turn that into a real utility service, billing and charging people actually for what they consume, not for what they've reserved in advance. And just scanning down here, you've got full control. The CPU affinity is what CPUs that particular virtual container is bound to. So here it's true, 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 meaning there are 4 CPUs available to the application of which it has access to all 4. If you were to change that, you could go true, false, and it would have access only to CPU cores 1 and 3, not 1, 2, 3, 4. And write down things like the number of file descriptors, the number of sockets. Is there a limit for the number of concurrent file descriptors that can be opened? Is there a limit for the number of sockets? All of these things can be arbitrarily controlled by the JVM. And here we have just another example of just starting up another application. In this case, it happens to be Bean Shell. We're all familiar with Bean Shell. Using console, you can attach and detach and reattach. It's a TCK certified JVM, so pretty much anything runs. And because it's virtualization inside the JVM, the applications don't know what's going on. It's completely transparent. Here it gets a little bit interesting. It's the last big feature demonstration here in slides. And that is looking at the extended virtualization. And here we have a picture of where we're running up Tomcat 2.7 by the looks of it in this example, but we're showing off the extended virtualization ability. And that's expressed here, and you can see that in this thing called the virtualization driver. And so we see here that while we're starting Tomcat, we've actually told the JVM through the configuration options that we want it to load Tomcat and we want it to load a virtualization driver. The JVM has found the virtualization driver for Apache Tomcat, and then we see here that when it goes to start Tomcat, what it actually starts first is the virtualization driver down to here, and then it starts Tomcat in the normal way that it would start Tomcat. And that virtualization driver uses the extended APIs in the JVM to tell the JVM how it wants the JVM to virtualize Tomcat. So we see here, virtualization driver for Tomcat, version 0.9, starting driver, okay, bang, and we're into Tomcat. And when we type list here, we see now that Tomcat's running in a virtual container. It's running actually in a special virtual container. We see the VCID there says PLAF. PLAF is a special virtual container, a numerical value of 0 that's reserved essentially for the domain 0, DOM 0 virtual container within the JVM. He has the authority and the permission to control all the other virtual containers, as well as change the sharing boundaries between them. And so we see then that when we move to deploy a web application, in this case it's examples.war, and I've just used a convenient helper function deploy that's built into JERSH for that purpose. I've deployed examples.war onto Tomcat, but surprise, surprise, when I type list, something strange has happened. I actually have 2 virtual containers now. I have one virtual container for Tomcat, and I have one virtual container for examples.war. And here's the kicker. Neither examples.war or Tomcat know. So the virtualization is invisible, it's done in the middle. And so here I now have the ability to start to control that particular examples.war virtual container by itself. And we see that the JVM actually recognizes now that the container type, the VC type, has changed. Whereas for Hello World it was Java container, now it's server container. If I wanted to write an ABC example, then I'd call it an ABC container. And so you can have as many different custom JVC types as you want, and the JVM will respect that. And we see here that we have very little memory used, we see no CPU consumed, and there's no memory, there's no byte sent or received over the socket interface. Well, of course there's not, because I've just loaded the server, I haven't exercised it. There's no HTTP traffic against this. So in the next slide, I'll press down now. In the next slide, we'll see what happens after we've done 50 concurrent HTTP requests against that servlet, and we see that the numbers change. So we can see them changing here. Suddenly more memory's been allocated to service those requests. The number of classes loaded has gone up by about 50. And we see down here that the bytes sent and received into that individual server has gone up. So the JVM is tracking this, and this is completely automatic inside the JVM, and it's transparent to the Tomcats or the JBosses and the WAR files, the AI files that you run. So that's kind of a short summary, a short demonstration. What I want to do now is introduce Derek Ennis from Push Technologies. He has had the fun job of playing with this JVM now for some number of weeks, so he's going to share with you his experiences as a real use case and the use case that him and his company are building behind this JVM. It's very exciting stuff. Derek, come on up.
Hello, so I met John about a month ago at Fight Club, which is a financial kind of IT conference in London. I heard a similar talk to this and got very interested. So my role at Push Technologies, so we're a small company, we're a British startup, we're about 6-7 years old. We take messaging, we basically provide it to last mile devices, so mobile phones. So we're typically working over the internet. Now, traditional messaging, where most people have a messaging background in, isn't really well oriented to the web. It's not oriented for mobile. On a mobile service, such as on my mobile phone, I've got between 0.5 and 4 megabits per second available to that device. So if I send an enterprise class feed to that phone, I saturate the network, I clog up the pipes, it doesn't work very well. So our product deviates in various elegant ways from traditional messaging to provide good, responsive, timely, relevant data, current data right now down to those devices. So we're kind of like messaging in that we're loosely coupled, we've got producers and consumers, but our protocol is very different under the hood. And this virtualizing these containers is very interesting to us because it allows us to scale how many applications we provide and the conditions under which those applications or services or data streams are provided out to external clients. So that's really what got me interested in looking at Waratek. So we've got traditional messaging that we know and love. It's typically stateless. You can't store state inside the engine. You can in ours. We also cache that data. So we cache this data in memory. So if I drop the connection, I go under a tunnel, and I connect when I get back to the other side of the tunnel, then I will know, the messaging system will say, well, here's the messages that you've missed since the last time you connected. And we can pick up where we left off. It's a very important feature when you've got very low fidelity in a network environment. And because we have this data in memory and we can send you differences or deltas and snapshots at various points in time, we can introspect that data so that we can further provide various intelligent data services on top of a traditional messaging-like set of APIs. And that's what we do. So that's where most of the intelligence comes from our version of messaging, which is oriented for this live, internet, unstable, unfriendly environment. How does Waratek fit into this? So I took our core product and I essentially run it in domain zero as a platform, and I can spin up various copies of this product. I can run different applications inside this system. So another difference or elegant deviation that Fusion has from regular messaging is you can plug your own behaviors right inside the heart of the engine. So I might have a set of interactions that are customer different, and I might want to change how I cluster something or how I distribute data geographically over the web for whatever reason. So I can basically write logic to put it in a diffusion archive, which is kind of like an enterprise archive or a web archive. Ours is for messaging or for distribution, so we call them diffusion archives. And I can plug it into the engine. Now this logic, this behavior is client code. I didn't write it and I don't trust it. I now have the ability to ring fence that into its own isolated container, manage and monitor that in various special ways. And that's a very exciting capability to have inside a JVM. So basically, in a nutshell, after 3 to 4 weeks of playing with Waratek, it basically just works. It does what it says in the tin. I can take regular Java code, deploy it inside the engine, and expect it to work the way regular Java code should work. And as I'm in the messaging business or the data distribution business, I don't have to worry about isolation. I don't have to worry about multi-tenancy. I don't have to worry about the high-density aspects of scalable deployments. Waratek gives me that out of the box. So I can now worry about how do I want to isolate or expose interesting APIs on top of the Waratek VM and expose the diffusion product in interesting ways for various clients that are using it in, to build the kind of data distribution products with the control that they want in kind of mission-critical operating environments. And it works very, very well at that. Okay, so here's an example. So one of the first things I did when I got the APIs is I got very tired of the interactive console quite quickly. So I wrote an application inside Diffusion. It exposes a web container. So I have a web UI. I can manage and monitor, control. I can spin up Diffusion instances inside Waratek via my mobile phone and via the web. So I can spin up a new instance of Diffusion with its own IP address and connect to it on my mobile phone. We have hot deployment, so I can hot deploy an application into that environment. And that might be an application that receives an FX feed or an equities feed and exposes that on a website so that you can connect to that over a mobile phone. I might deploy apps into QA development or UAT environments. So instead of now needing 4, 5, or 6 boxes, I can get 4 or 5, 6 instances onto a single box, which makes it much easier to run multiple different QA tracks at the same time or performance benchmarking tracks at the same time or whatever, and deploy multiple different multi-tenant isolated environments. So if you're in a software company like we are and you've got a proof of concept running in China or in Africa and you don't have manpower there, you can spin up an instance, give someone an IP address and say, have at it, have a play, here's our SDKs. And it gives you that human scalability or business scalability that isn't possible if you're reliant on setting up infrastructure or reliant on the people you're working with setting up infrastructure and deploying your software in their environment when they don't have the relevant skills yet. So there's a lot of human factors that you can actually scale by using something like Waratek. So it's pretty cool stuff. It gets really exciting, though, when you put this in the context of the cloud, because it's built from the ground up to do that. It's got multi-tenancy, it's got isolation, and it's elastic. So I've got my product, my data distribution product, running in domain 0, and I've got my product also running in the JVCs and the virtual containers in a different way. I deploy a special app inside domain 0, and that allows me to control the underlying JVC instances. Then I'll give you the IP address for that, and you'll deploy your own applications into that context. So I can get this special domain 0, this privileged container, talking to other privileged container in a cloud or in multiple cloud environments. So now you're not only elastic on a single box, you're elastic across the cloud or a set of clouds. And it really opens up the possibilities for building some very interesting deployment environments with very fine-grained control over independent pieces of code that might be contributed by other people or operated by other people. And that's really where the power of this actually gets brought to bear in the real world, is it enables you to build all of this, but without the cost of spending a couple of years building all of this, which is pretty cool. That's it for me.
I think we've wrapped up. Thank you very much.